Hey guys, hope everybody's doing okay. What we're going to do today is get started with our next unit in the course, which is on chemical thermodynamics. And this unit really focuses on energy and the transfer of energy between substances. It also has to do with the amount of energy available for different processes to occur. So we'll take a look at all that as we progress through this unit, but today we're going to start with some basic calculations with heat or energy and how much it takes to heat up or cool down various substances. So on the screen in front of you, you can see that we have two beakers with two different substances in them. So the beaker on the left is 100 grams of water, and the beaker on the right is 100 grams of carbon tetrachloride, CCl4. Both of these are at 25 degrees Celsius. So the question is, does it take the same amount of energy to heat the contents of each beaker up to 26 degrees Celsius? So let's take a look at it and find out. We could predict whether it would be the same amount of energy. I mean, we have two different substances, but they're both at 100 grams, and they're both at 25 degrees Celsius to start out. So let's see how much it takes for the water to get heated up from 25 to 26 Celsius. Looks like it's 418.4 joules worth of energy, and the carbon tetrachloride is 88.6. So if you predicted that the energies would be different, then of course you're correct here. And the reason being goes all the way back to the first couple units of the course, where we looked at the structures of these various molecules and the intermolecular forces of attraction that hold them together. So with water, we have hydrogen bonding as the primary force of attraction, and for carbon tetrachloride, we have London dispersion as the primary forces of attraction there. So in order to get the particles in water to move around faster, which is what happens as you go from 25 to 26 degrees, we have to increase that average kinetic energy. It takes a little bit more work for that to happen because that hydrogen bonding that water has is so strong. With carbon tetrachloride, that London dispersion force overall is a weaker intermolecular force, so it doesn't take quite as much energy to get those particles moving a little bit faster and get that kinetic energy to raise a little bit to go to 26 degrees Celsius. So what we call this is the heat capacity. Heat capacity is the amount of energy needed to raise the temperature of a sample by 1 degree Celsius. So this is just, in general, a sample, right? So the sample could be 100 grams, it could be 200 grams, whatever. But you want to raise the temperature of that sample you have by 1 degree Celsius. This is related to the next slide, where we're going to focus on a smaller amount, like a smaller sample size, and we're going to be more consistent with our sample size as well. So here we go. We have our 100 grams of water on the left, where we already know it's 418.4 joules of energy in order for that to go from 25 to 26 degrees Celsius. And on the right, we only have 1 gram of water at 25 degrees Celsius. So we have 1/100th of what we started with. We have 1 gram versus 100 grams. So the energy that it should take to heat up 1 gram of water should be 1/100th of what we initially had. So 4.184 joules of energy to heat up 1 gram of water from 25 to 26 degrees Celsius. This is known as a specific heat, and we're going to use this a lot throughout the course of the unit. So this is the amount of energy needed to raise a 1 gram sample of a substance by 1 degree Celsius. Okay? So again, we're talking about a 1 gram sample here. The reason why we choose a 1 gram sample is so we can have basically a big list of specific heats for various substances. If we kind of standardize the sample size to 1 gram, increasing the temperature of 1 gram by 1 degree Celsius, then we can make a list of these specific heats, and we can see which substances require more or less heat to raise their temperature by 1 degree Celsius. We can relate this to a calorie. So a calorie is the amount of energy needed to raise a 1 gram sample of water by 1 degree Celsius. So we can see on the screen here we have 4.184 joules of energy to raise 1 gram of water by 1 degree Celsius. That is the same as 1 calorie. So sometimes we may need to convert between joules and kilojoules and calories, and in order to do that we need the conversion factor. So here it is. 1 calorie is equal to 4.184 joules of energy. All right? So just factor label it if you need to convert from calories to joules into kilojoules if necessary. So here's a table of some specific heats. You can see them on the screen here. So we have some elements on the left, materials on the right, and you can see wood, cement, glass, granite. Some of you may have granite countertops in your kitchen, and steel. The greater these values, the more energy it takes to heat them up by 1 degree Celsius. The smaller the value, the easier that process is going to be like, the less energy it's going to take to heat up a substance. So there's a couple I want to highlight here. Water is up here, which is 4.184 joules per gram degree Celsius. So it's 4.184 joules of energy to heat up a gram 1 degree Celsius. That's why it has joules per gram degree Celsius. The units in this unit are really, really, really important. So you want to make sure you are aware of if it's joules, kilojoules, grams, whatever. You know what I mean? So you want to be very, very careful with that. You're going to compare that to ice at -5 degrees Celsius of a 2.1 value. So it's interesting that both of these are water, but water in the liquid form versus the ice form has a different specific heat. The reason this difference occurs is because obviously water in the liquid form has more movement, right? The particles are moving around freely over one another, and with ice they're not. So if you're heating up some ice, it doesn't take as much energy to heat up ice by 1 degree because the particles are relatively stagnant. So you're heating up one section of it, a smaller amount of surface area is being heated. For water in the liquid form, the particles are in constant movement. So as you heat that, you have more surface area that you need to heat. So it takes more energy to get those particles moving with a higher kinetic energy value. So that's why the difference is between ice and water here is liquid water is 4.184 versus 2.1. It's kind of a neat little thing to look at there. You should memorize waters. You're going to use it a lot when we do some calorimetry examples and when we do solution calorimetry as well. So that's something that we should definitely know. 4.184 joules per gram degree Celsius. You don't even really have to actively try to memorize that. You're just going to do so many of those problems that you're going to definitely know what it is. Some of this is really interesting because if you have maybe tile in your kitchen or you have tile in your house and you have carpet in your house, and say your house is set to 70 degrees for your thermostat, the tile is 70 degrees and the carpet is 70 degrees. But if you have bare feet and you step on the tile, your feet are really cold. If you step on the carpet, they're not. How could that be? They're both the same temperature. They're both 70 degrees. It all has to do with these specific heat values. So the tile heats up or cools down a lot faster. Okay, so when you step on the tile with your bare feet, all that energy from your feet, that's being transferred to the tile, all right? So your feet feel cold. Where you step on carpet, it's a better insulator, obviously, right? So the transfer of energy isn't as drastic, so your feet don't feel as cold, even though they're both substances at the same temperature. So it all has to do with that transfer of energy and what substances you require more or less energy to heat up. So I think that's really cool as well. So let's do a practice calculation here. We have a 25 gram sample of copper. We're going to heat that up from 25 Celsius to 50 Celsius. How much energy does that take? We're going to introduce a new formula for you here, so make sure you write down what these different variables mean. Q stands for energy or heat. All right, so let's make sure we write that in there. So Q is energy or heat. M obviously is going to stand for mass in grams. Okay. We already had on the previous slide or two that C stands for specific heat. So specific heat. And the delta T is your change in temperature. So this is really important here. Your change in temperature is going to be your final temperature minus your initial temperature. Okay? T final minus T initial. That's really important here. So it's not initial minus final, it's final minus initial, where you end minus where you started. That's going to make a big deal. That's going to make a big difference if your answer is obviously positive or negative, especially in this case. So we want to make sure we're okay with that. Specific heat of copper is 0.385 joules per gram degree Celsius. So much easier to heat up a piece of copper by 1 degree Celsius than it is to heat up a gram of water by 1 degree Celsius. So the specific heat for water was 4.184 joules per gram Celsius. And then for copper, it's 0.385. So way less energy required to heat up 1 gram by 1 degree Celsius. So this is pretty simple. All we have to do is plug all this in to our Q equals MC delta T equation and see what we end up with. So let's take a second and actually do that and see what we end up with here. So let's set it up over here. Q equals MC delta T. Q equals M, so your mass is 25 grams. Specific heat, 0.385 joules per gram degree Celsius. It's really, really important to include your units in your calculation. Okay, so you know I'm all about that ever since you in Chem 1. We need to continue that here so we can see what units cancel to make sure our answer makes sense. Our delta T is going to be 50 degrees minus 25 degrees. Okay, let's simplify this real quick. So we end up with 25 grams times 0.385 joules per gram degree Celsius. This is going into the piece of copper here, sorry. And then our delta T was 25 degrees Celsius. Okay, look what happens. Grams is here on the top, okay, cancels out with grams here at the bottom in our specific heat. And you have Celsius here, if you can see it, Celsius is here on the top. That cancels out with the Celsius in the denominator here in our specific heat. Look at the only unit that's left. The only unit that's left is in joules, okay? So the grams cancel, the Celsius cancel, that's why it's really important to look at that that way. Looks like our answer should have 2 sig figs, and we end up with 240 joules of energy to raise 25 grams of copper by 25 degrees Celsius, from 25 to 50, all right? Your Q value is a positive value for this one. Energy is going in, okay, it's an endothermic process. Energy is required to heat up this piece of copper. So that's what we want to look at here. We're going to wrap it up with this type of problem, which is how much energy is required to raise 2 liters of water from negative 20 Celsius to 120 degrees Celsius. So you might say, let's just use Q equals MC delta T. But we can't. Oh, we could use it for part of this. We can't use it for the whole thing. All right. What we have to do here is recognize what happens as we go from negative 20 Celsius to 120 Celsius. Your Q equals MC delta T only accounts for kinetic energy changes because you need to have a delta T. You need to have a change in temperature. Well, as you go from negative 20 Celsius to 120 Celsius, you eventually reach a couple phase changes, right? When you have a phase change, you don't have a change in temperature, but energy is still being put in to that process, right? So as ice is melting, that's what's happening here. Once you get from negative 20 Celsius, once you heat that up to 0 Celsius, the temperature stops during a phase change. We talked about this before. Once that temperature stops, you're still like heating that substance up until all the solid has completely melted into the liquid form. And then the temperature goes up again. So what we need to do is use a molar enthalpy or molar heat of fusion, which we have talked about before. That's the energy needed to change 1 mole of a substance, 1 mole of a substance, not gram, but 1 mole from a solid to a liquid. And we have our molar enthalpy or molar heat of vaporization. This is the amount of energy needed to change 1 mole of a substance from a liquid to a gas. At your phase changes, that's what's happening. We're changing from a solid to a liquid or from a liquid to a gas. And if you could visualize the heating curve, which I'll show you on the next slide or two, you'll see that. During those phase changes, this is the type of information that we need. Okay? So look at your heating curve. See if any parts of it are labeled. So you have your A to B is your solid, and we've been through this before in a different part of the course. Phase change is our melting, solid to liquid between B and C. It all turns into the liquid, and then the liquid gets heated up. We have a delta T, a kinetic energy change here. We have vaporization, and then we have a gas form. So the kinetic energy does not change during a phase change, which we've talked about. All the energy goes into breaking the bonds, like those, I wouldn't even say bonds here, I would say, like if it's water, it's hydrogen bonds, right? Those intermolecular forces, those forces of attraction are being broken here. They're being broken here and here. That's why there's no change in temperature. The particles are not speeding up there. So between A and B, you have a delta T. Between C and D, you have a delta T. And between E and F, you have a delta T. So you can use Q equals MC delta T in this location, and this location. Okay, here's where we can use Q equals MC delta T. Otherwise, we can't. So in this location here and here, we have to use, oh my goodness, we gotta go back here. We have to use the molar enthalpy of fusion when you go from solid to liquid, or liquid to a solid, right? And the molar enthalpy of vaporization if you go from a liquid to a gas. So delta HF or delta HV. All right, so here you have delta HF at this location, and then over here, this location here, you have delta HV. So usually those are given to you. You may have to find them, but you'll have enough information to do that if that's the case. So let's go through this practice problem. It's quite lengthy, so I have a couple blank slides here to go through it with you, and we'll go from there. All right. What I like to do is get a game plan first. All right. So I write up my game plan, and then we go from there. So you should have some space on your packet to do this. And I have the solution in front of me here, so we'll go through and knock it out, and then you'll be able to do a couple of these practice problems without my help, hopefully. All right, so we know that. Okay, how much energy is required to raise 2 liters of water from negative 20 Celsius to 120 Celsius? So you need to visualize your heating curve, and again, I'll go back to it here. Your melting point or your freezing point is at 0 Celsius, and your boiling point is at 100. So for this process, like say negative 20 is here and 120 is here, we have to go through 2 phase changes to make this happen. All right, so let's go through what's going on here. The first step of this process, I'm going to label step 1. I need to heat up my substance from negative 20 degrees all the way to 0 degrees. Because once I hit 0 degrees, I'm at a phase change point, okay? Once I hit 0 degrees, the temperature doesn't change anymore, it flatlines, so I have to use a different equation then. So what I like to do is write down what's going on first, heat from negative 20 to 0, and in order to do that, since there is a temperature change here, I'm going to have Q equals MC delta T as the main formula I need to use here. Okay, so let's go through and figure out how much energy that part of it takes. So we'll go through and figure this out real quick. So Q equals M. Now be careful because 2 liters of water is 2,000 milliliters. Okay, and then the density of water we're just going to say is 1 gram per milliliter. So you get 2 liters into 2,000 milliliters. The density is 1 gram per milliliter, so you have 2,000 grams. The specific heat for, now be careful here, this is the specific heat for ice. Okay, remember I showed you on that slide earlier that the specific heat capacity for water in the solid form is different from the liquid form. So this value is given to you. It was around 2 point something. It varies depending on what textbook or what chart you look at. But the one I looked up for the specific heat, the C value for water in the solid form is 2.03 joules per gram degree Celsius. Okay. My delta T is going to be T final minus T initial. So I have 0 Celsius minus negative 20 Celsius. And I get my answer. So I'm just going to tell you what it is. So you can type it into your calculator without making a dumb mistake, obviously. And you're going to get, in terms of joules, you're going to get 81,200. All right, so that's a lot of energy. 81,200 joules for part 1. All right, so let's move on to the next part of this. All right, so far we've heated that up 20 degrees. You're going to say, well, that's a huge number, 81,200. That makes sense, though. You're raising 2,000 milliliters of water 20 degrees in temperature. And the specific heat per 1 gram for 1 degree is 4.184 joules. So it looks reasonable. Okay, it should be a lot of energy. Now, the second thing we have to do is we need to melt the ice at 0 degrees. Okay, that's a phase change. Okay, so for a phase change, we're going from, in this case, a solid to a liquid. And if you remember on the previous slide, that is delta HF. Okay, I would look up the delta HF value. So you're going to have a chart with all these in it. If you look up the delta HF, the heat of fusion of water, you're going to get 6.00 kilojoules per mole. All right? So we have 6.00 kilojoules per mole. The units here are key, all right? So we're in kilojoules here. I need to make sure I'm consistent between the different parts of this process. What I need to do then is convert 6.00 kilojoules per mole into joules. What I need to do then is figure out, I need to cancel out moles here, right? I need to figure out how many moles of water I have. That's easy to do because I have 2,000 grams of water. I could just convert 2,000 grams of water into moles of water and then convert the kilojoules into joules there. All right. So it takes 6 kilojoules of energy to melt a mole of ice. All right. We need to figure out how many moles I do have. So I'm just going to put that all right here for you. So we have 2,000 grams of water. I'm going to convert that into moles of water. So we're going to cancel out the molar mass, 18.02 grams in 1 mole. Okay, so look what happens. Your grams of water obviously cancel out here. Oops, I shouldn't have put it through the whole thing. Your moles cancel there and there. Okay, and now I need to convert to kilojoules. So I have 1,000 joules over 1 kilojoule. All right, kilojoules on top here, on bottom here, they cancel out. So your amount of energy, and of course this is Q, so Q is equal to, on this step, it's a lot. Okay, it's 666,000. 666,000 joules. Now we're in joules here. We could convert to kilojoules to make this look a little less big. It's still a lot of energy. It takes 6 kilojoules to melt a mole of ice. So once we figure out how many moles of ice we have a lot of moles because we have 2,000 grams of it, and it's 18.02 grams per mole. Should be a huge number, and it is. Okay, so let's go to step 3 then. All right, once step 2 is complete and all of the ice has melted, we need to go to step 3, which is heating it up until our next phase change. So what we want to do for step 3 is we want to heat, and we have liquid water. Okay, now it's all liquid, so it's important. We need to heat all of our liquid water from 0 Celsius until our next phase change, which would be the boiling point. So that is 100 degrees. Okay, I know I have to at least go to there because I need to get this to 120. Okay, so we have to go through another phase change here to make that happen. So anytime that occurs, anytime we have a delta T, so we're in that big middle part of the heating curve from the previous slide, we are at, or we have to use Q equals MC delta T. So let's go ahead and do it. We have Q equals MC delta T. I didn't have to write it again. So our mass, we still have 2,000 grams. Now our C value, the specific heat, we're at liquid water now. So we can go to what we should know, what we know for water is 4.184 joules per gram degree Celsius. And our delta T is 100 degrees minus 0 degrees. So our T final minus T initial. If you go ahead and solve that, our unit should be in joules here, and our Q value comes out to be 837,000 joules. Okay. You may be asking where I'm getting my sig figs from. I just kind of picked 3 sig figs for this one. So your answer may vary based on mine or the answer keys that are posted based on sig figs. Okay, we're almost done here. Kind of. We still have 2 more steps to go, but we'll go through them a little bit faster here. So keep all these in mind, and let's go to do our last 2 steps here. Step 4, since we have now heated up to 100 degrees Celsius, we need to evaporate all of it. So we need to evaporate our 2,000 grams at 100 degrees Celsius. So At 100 degrees Celsius, it starts to boil, right? So we're trying to evaporate all of our water, get it all into the liquid state. That takes a lot of energy. That's a phase change, right? So that is our molar heat of vaporization, okay, which you can just look up. So if I look it up for you, which I did, our molar heat of vaporization is 4.07 kilojoules per mole, okay? So, I'm sorry, 40.7. 40.7 kilojoules, sloppy, per mole. Okay, you're going to say, well, wow, this is huge. Right? This is a lot more than the 6 kilojoules per mole for my heat of fusion. And you're exactly right. We talked about this before in the course as well. To go from a solid to a liquid, the particles don't have to separate all that much, right? They just have to start to move a little bit more freely over one another. But in order to go from a liquid to a gas, we have to break all the intermolecular attractions, because gases have basically no attractive forces at all. So we have to, that's going to require a lot more energy for that to occur. All right, the rest of it's the same as step 2. We just have to cancel out moles and convert to joules. So we'll just do that same step here. So we had, again, 2,000 grams of water. Cancel out grams, 18.02, go to moles, and then convert into joules. So 1,000 joules over 1 kilojoule. Kilojoules cancel, grams cancel, and moles cancel. There we go. So plug in your calculator, and you end up with lots, okay? 4,520,000 joules of energy. That makes perfect sense because your molar heat of vaporization here is 40.7 compared to 6 for step number 2. And step number 2 took almost 700,000 joules of energy. So this should take a whole lot more. Okay, last step. We're at 100 degrees Celsius. We can keep heating that up to 120. So we want to heat 2,000 grams of water. Now we're in the gas state now, okay, from 100 degrees all the way up to 120 degrees. So again, when we do something like this, we have a delta T. So we have Q equals MC delta T. Plug everything in. You have 2,000 grams. Your specific heat has to be for water in the gas state, which I looked it up. It's 2.00 joules per gram degree Celsius. And your delta T is 120 minus 100, T final minus T initial. Plug it in your calculator, and you end up with 80,000. I'll put a line over that to give it an extra sig fig. 80,000 joules worth of energy. Okay? So we have to finally add all these up, okay, and see what we end up with. And once we do that, we have our total process here of going from negative 20 degrees Celsius to 120 degrees Celsius to figure out how much energy the whole process takes. So if you add them all up, your Q value is equal to, I'll put it in scientific notation for us, we have 6.18 times 10 to the 6th joules of energy. All right? So quite the process here. Now I could have given you an example where it was like 2 steps. That maybe would have been a little bit nicer. But now we know how to do the longest type of problem that you'll have to do with this process. All right. So to conclude all this, you have during your phase changes, you can't use Q equals MC delta T. All right. So that's where the 2 X's are on here. So between B and C and D and E, you can't use Q equals MC delta T there because there's no delta T. And between A and B, C and D, and E and F, you have to use Q equals MC delta T. That's where your kinetic energy change is occurring. All right. In your notes, there's some tables, or in your packet, there are some tables with these values in it that you need to use to go through and solve a lot of the problems. Okay, so there are some problems in your packet that you are able to tackle now, and we can talk about some more in class if we need to. All right, guys, thanks.